Hello, good morning. William, can you hear me okay?
Yeah, loud and clear.
Great. All right. So we had some intermittent internet issues in the last class. I think the broadband width is not great in Marcus right now. So hopefully it doesn't get too glitchy, but if it does, let me know. When I switch over to the dot cam, I am going to turn off my webcam so you won't be able to see my face to try to keep the bandwidth as stable as possible for you guys. So I apologize in advance for any glitchiness. Couple quick announcements. So Thursday is Veterans Day. So we remember and we thank all our military members for their service. And so we do not have class on Thursday. There's no school. So I won't see you guys again until Tuesday. That being said, we do have our I have the hiccups. Sorry. We do have our mini quiz tomorrow on global maximums and minimums, which we'll talk about mostly today. And then on Sunday, you'll have a mini quiz on the profit, revenue, and cost applications. So we started those last time, and we will also finish those today so that you are ready for Sunday's mini quiz. For the profit, revenue, and cost, I do want to encourage you to look back at chapter 2.5 and 1.4, because there's certainly things that come up from when we first learned about economics that are going to sort of circle back and be applied to what we're talking about now. So that's what's sort of on our radar. That's what's coming up today. So in terms of order, I think we're going to do the last problem from profit, revenue, and cost first. We did the other problems at the end of last class. So we'll just sort of finish that up, and then we'll do global maximums and global minimums. So I'm going to go ahead and switch over to the dot cam. Give me 1 second here. Get that straightened out. And then I'm going to turn off the video for me, and hopefully everything will stay stabilized, but let me know if it doesn't. So for our last example here, this is sort of a common type of problem in which we need to use what we know about local maxes and mins to solve the overall problem. So here,
Adina?
Yeah.
So you actually cut out for a few seconds there.
Oh, okay. So I'm saying this is a sort of common problem where we're selling something and we need to understand demand before we can even answer the question about maximizing revenue. So the situation is this: a theater has 1,000 seats, and when they set their ticket price to $10 per ticket, the theater sells out. Okay, so they sell all 1,000 seats. Every time they raise the price by $1, so for each additional dollar they charge, the number of seats is reduced by 50 that people are willing to buy. Okay, so for the first part, part A, we need to find a linear equation that fits this data, right? So we need to think about how we can write this information as 2 points and how we can then turn that into a linear function, right? The line that connects those 2 points. Instead of using the variables x and y, we're going to substitute in Q and P, quantity and price, into our equation. And this is called the demand equation. And so I'm going to write down one of the points here just to give you a sense of what I'm talking about. So I'm going to write the one that is given to us. So when the price is $10, we sell 1,000 seats. Okay. What you're going to need to do is figure out a second point based on the fact that for each additional dollar charge, if we raise the price by $1, we reduce the number of seats we sell by 50. You're going to use that to generate a second point. Once you have that second point, you're going to find the equation of the line by looking for the slope, right? You can start with y equals mx plus b, then figure out what is the new variable. Is it quantity or price based on the order here? Once you have your equation, then you can move on to parts B and C. Part B says use your equation from part B, which is set up here, P times Q. Set up the revenue equation by substituting the demand equation in for Q. That's a typo. If you have it printed out, that's supposed to say Q. This will make more sense once you have your demand equation. You're substituting it in here. And then we are able to use derivatives in part C to look at what the price and quantity that will maximize our function is. So start trying this, even if it seems like you're not really sure what to do. I feel pretty confident you can find the equation of the line, and then see if it makes sense, as you sort of go along. So I'm going to give you 3 minutes to try this out. Then we'll go through it together, and then I'll talk for a minute about sort of alternative ways we can ask questions about this scenario. Okay, so take 3 minutes, and I will go over it then. All right, take about 30 more seconds. All right, so let's take a look at the steps here. And so one of the things I want to mention sort of at the beginning is sometimes the question is just the question for part C. But even if the question just says find the price and quantity that maximize revenue, you still have to do parts A and B to be able to answer part C. So even if it doesn't explicitly spell it out, we still need to do these steps. Okay, so we have the point 10 comma 1000. And now we also know that for each additional dollar charged, the number of seats is reduced by 50. So if we increase from 10 to $11, we reduce from 1,000 to 950. Okay, so we go up $1 in price, down 50 seats. So now we have 2 points, and we want to find the equation of a line. So of course, we're going to need slope. So to find slope here, we're going to do change in y over change in x. So 1,000 minus 950 over 10 minus 11 is going to give us a slope of negative 50. Okay, so we have y equals negative 50x plus b. We need to find b, so we substitute in one of our points. So we have 1,000 equals negative 50 times 10 plus b. Negative 50 times 10 is negative 500. So we add that over, and we get b equals 1,500. So in terms of y equals mx plus b, we would have y equals negative 50x plus 1,500. But we want to rewrite this with q and p. So maybe you started that way. That's totally fine. Or you can substitute in these variables at the end. So we need to figure out, where does quantity go and where does price go, right? Q and P. So if you look at our points here, points are typically written X, comma, Y, right? And we know that $10 is a price and 1,000 tickets is a quantity. So the way we set this up, our P is going to substitute in for X, and our Q is going to substitute in for Y. So we have Q equals negative 50P plus 1,500. Okay, so this equation is called the demand equation. And what the demand equation does is it sets up a relationship that says, hey, if you charge this amount, so $10, $11, $12, consumers will buy or demand this amount, right? That's why it's called the demand equation, because it helps you understand how many will be bought, how many will be demanded based on different prices, okay? One of the key things that we need to think about here in terms of price is that typically when we think about revenue, we treat price as a constant, right? So price is $10. What if I sell them for $10? What if I sell them for $20? What's happening in this scenario is that both quantity and price are being treated as variables. They can vary. They're related in this way, but they vary in both Q and in P. So this makes it different than the other revenue type situations that we typically look at. Okay, so for part B, now we need to set up a revenue function that incorporates the fact that both P and Q are variables, right? So revenue equals price times quantity. Now price can vary and quantity can vary, which means that technically right now, this is a 2-variable equation. We don't know how to do multivariable calculus, right? So what the demand equation does for us is it says, okay, instead of Q, we can substitute in what Q equals in terms of price. So negative 50P plus 1,500. Okay, so that's our Q. That's what Q equals. The reason that we want to do this is because now we only have one variable, the variable P. And we've brought it back to single variable, which is what we do know how to work with. So I'm going to simplify this by multiplying the P through. So I have negative 50 P squared plus 1,500 P. So that's part B, is setting up the revenue equation in terms of one variable. Okay, and again, we get it down to one variable by substituting in the demand equation. Part C wants us to maximize the revenue. So what we're going to do is we're going to find the first derivative and look for critical points here. So the first derivative, we're going to get negative 100p plus 1,500. And I want to know, when does that equal 0? So I bring the negative 100p over, divide by 100, and I get P equals 15 is a critical point for this derivative. Now, I want to make sure that it's a maximum. I don't want to accidentally minimize my function. So if I look at the second derivative here, I get negative 100. Remember, if the second derivative is negative, the original function is concave down, so it is a max. Okay, so a price of $15 will maximize my revenue. Part C asks for the price and quantity. So now this $15 has to go back into the demand equation so we can figure out how many tickets we will sell at a price point of $15. So if I were to plug in a 15 here, I'm going to get Q equals 750. Okay, and again, that's because I plugged this back into the demand equation. So at a price of $15, I will sell 750 tickets, and that combination maximizes my revenue. Now, I didn't ask you to find the maximum revenue, but if we wanted to actually figure out what the revenue was, we would multiply price times quantity. So 15 times 750 will give me $11,250. That is the maximum revenue. And if I compare that to some other information I know, this is looking pretty good that I did my work right. Because if I come up here, for $10 a ticket, I sell 1,000 tickets. 10 times 1,000, $10,000. That's less than this revenue, right? So even though I'm not filling all the seats, I make more money because the price is more expensive here. This is the price and quantity that's going to maximize revenue. So these are all the types of things we can ask. We could ask, what is the equation? We could ask, what is the price that maximizes it? What is the quantity sold when it's maximized? What is the revenue, right? So all of these three numbers are fair questions based on this situation. So this will come up whenever you have an example where you are trying to figure out how to set the price based on the quantity, right? The demand. So this is sort of common. We could say something like, apartment complex has 1,000 apartments, and when we rent them for $100, we rent them all. And for each additional $100 we charge, the number we rent goes down by 50, right? So any scenario where you're relating price and quantity, you have to start with the demand equation and then work from there, okay? So that is the last example from the cost revenue profit section, 4.4. And so now we're going to transition over and talk about global maximums and global minimums. All right. So we've done some work on local maximums and minimums. And I'm actually going to start with this picture, and then we'll go back to the definition in a minute. And just remind you where our local maximums and minimums are and how we defined those. So here, our local maximums and minimums, we said happen at critical points, and we said there can be multiple of them. Here we have 2 local minimums and 1 local maximum. And we said that it's a high or low point in a small area, right? That's what the word local told us. So now what we're going to be talking about is something called global maximums and minimums. So a global maximum, right? A function is said to have a global maximum at P, so at some X value, if f of P, so the Y value, is greater than or equal to all the values of f of X. So what does that mean? That means that if you have the highest Y value, that is going to be the global maximum, right? Because it's equal to all the values. So it's greater than all of them, not just the nearby, but all of them. So if we were looking for a global maximum on this picture, this is the one with the highest Y value, okay? So the global maximum here is 2. Why is it 2? Because when we define a global maximum, we define it by the Y value, Okay, so the global maximum is that y value that is the highest possible y value for a function. Similarly, the global minimum is going to be when you have a y value that is less than or equal to all the values here. So we're looking for the lowest y value, which happens right here. So the global minimum, let's see, that looks like it's right about 0.5, right? About halfway between 0 and 1. So what is, how do I say this? What is similar about global max and mins to local max and mins, and what's different? Okay, the first big difference is how we define them. So global maximums and minimums are defined by their y values. Whereas when we talk about local maximums and minimums, we're always talking about where they are. So we're talking about them in terms of x values. Now, I want to point out here that this global max at 2 happens at the end point, and the global minimum here happens at a critical point. Okay, that's not a coincidence. It turns out that our global values, if they exist, will always happen at either an end point or a critical point. Okay, now 2 other things that are true. So global extrema, which are global max and mins, are defined by their dependent value. So even though I'm pointing out here the global max is 2, the global max is 0.5, I would say 80% of the time, that's what we're doing. Occasionally, the question will ask you, where does the global max happen? And if it asks you where it happens, it's looking for the x value. If it asks you what is the global maximum minimum, then we're looking for the y value, okay? The second thing is functions can only have one global max and one global min, or it might not have any at all, but it cannot have multiple global maximums and global minimums. And so I want to draw another picture just to give you sort of an example of why this might be confusing, but how we sort of work with it. Okay, so let's say this is, I don't know, 4. Say we have a function that looks like this, right? And let's say that these peaks are the same height. You may think that there are 2 global maximums because there's 2 places it happens. But the global maximum here is the value 4. There's only one global maximum. It's 4. It can happen at more than one place. So it might happen at 2 and at 5. However, the global maximum, there's only one. It's 4. Okay, so since we're defining it by the y value, it can only have one, because if you said it was at 4 and at 6, that means that there's a y value of 4 and 6, and 6 is bigger, so it would really just be 6, right? So even though it can happen at more than one place, since we define it by the y value, there's only one global max or min stated, okay? So we're going to take this information and we're going to start off by trying some of the algebraic problems. And so I want to remind you sort of what I just said and turn it into a process. So we said that global maximums and minimums happen at critical points or endpoints. How do we get endpoints? Well, if we have a picture, sometimes the graph stops and we can figure out what the endpoints are. And sometimes we're given an interval. So we're told that x has to be between this number and this number, okay? What does that mean for our process? That means that you have to make sure that your critical points are on that interval in order to be able to use them. If they are, then the process looks like this, okay? Step 1, you find the critical points of your function. So whatever the function is, you figure out what the critical points are, okay? After you have your critical points, you are going to set up a list of critical points and endpoints. So x equals 1 and x equals 5 and x equals 7, whatever they are, right? Critical points and endpoints. And then the third, you're going to test critical points and endpoints in the original function. Okay, because we are trying to figure out the highest and lowest y value of the original function. So that's where we have to test them. Okay, so you're going to try the first one, but I'm just going to give you a couple of pointers. So I'm going to write this function a little bit bigger just because it looks small to me on the screen. So x cubed minus 9x squared minus 48x plus 52. Okay, first step, you're going to find the critical points. So you're going to find the first derivative, set it equal to 0, right? Once you have those, you are checking them against the interval. Here, the interval is -5 to 11. You can only use critical points that are between -5 and 11. Okay. Once you have those critical points, you're going to make a list. And your list is going to be your critical points and also x equals -5 and x equals 11. Those are the endpoints. You're going to take each and every one of them and plug them back into the original. And so next to your x value, you will have the corresponding y value, that dependent value. Once you have those y values, you have to figure out which one is the biggest and which one is the smallest. That's your global maximum and your global minimum. Okay, so I'm going to give you about 3 minutes. Try this out, see if you can follow this process, and then we will go through it together. All right, take about 30 more seconds. All right. So let's very carefully walk through the steps of this. And these are going to be sort of the common steps for a lot of these types of problems that you'll be doing. So again, the first step is that we're looking for the critical points, which means that we're going to take the first derivative and set it equal to 0. So the first derivative here, we have 3x squared minus 18x minus 48. We want to know, when does that equal 0? So again, you have a couple choices here. You can use the quadratic equation. I factored it. I just prefer to try to factor if I can, but that's just a preference. Whatever makes most sense for you is totally fine. So this factors down to x minus 8, x plus 2. So that means I have a critical point at x equals 8 and x equals negative 2. Okay, so what I need to do now is I need to go to my interval to make sure that both of these critical points are on this interval. Well, 8 is certainly between negative 5 and 11, and negative 2 is also between negative 5 and 11. So I can use both of these critical points in my list. Okay, so now step 2, I'm going to make a list of my critical points and my endpoints, right? So I have x equals 8. X equals negative 2. Those are my critical points. But then I also need my endpoints. So x equals negative 5 and x equals 11. So those again come from this interval right here that tell me my endpoints, which I'm abbreviating EPs for endpoints. Okay, so step 3 now is I need to take each of these points and plug them back into the original so that I can get the corresponding y value, right? And I did this on my calculator, so don't feel like you need to try to do this out by hand or anything crazy like that. I mean, you can if you want to, but I just plugged them in. So if you plug in x equals 8, I got negative 396. When I plugged in negative 2, I got 104. When I plugged in negative 5, I got negative 58. And when I plugged in 11, I got negative 234. Okay, so now I have my list of y values and I want to compare them. I want to know which one is the highest and which one is the lowest. So starting with the biggest, I think of a number line that goes up and down. And I see that y equals 104 will be the highest y value on that list. So my global max is going to be 104. And then I look at these numbers again to figure out which one's going to be the lowest on a number line. And I see that negative 396 is going to be there. So my global min equals negative 396. Okay, so that's what the process looks like. I find my critical points. I make sure that they're on my interval. If they're not, I just cross them out, throw them away. I make a list of my test points, which includes my critical points and my end points. I plug them back into the original, and then I compare these dependent values. Okay, the biggest one is my global max. The smallest one is my global min. So hopefully that process makes sense. So we're going to try 2 more that basically have the same structure. You know, we're just going to practice the algebra. What you'll notice in the next 2 examples, the first one has, you know, a similar algebraic feel, but for the second one, what you'll notice is that we have to do something. Yeah.
Oh, sorry. You froze when you said we're going to try 2 more.
Okay, so we're going to try 2 more where this first one, example 2, is very similar in algebraic structure. So when we take the derivatives, it's going to be very, very similar to the first one. But you have to make sure you answer the question the way it's being asked, which is a little tricky. And then for example 3, this one has a different type of function. So when you do the derivative, I'm just going to rewrite this because it's a little small. When you do the derivative, you will have to use a quotient rule to find those critical points. Okay, so I'm going to give you about 5 minutes to try these 2. We're going to be applying the same processes up here. I'll move it down a little to have our 3 steps and see if you can answer the questions for each of these. So notice that, for example, 3, we're just looking for the global minimum or just the global maximum, I'm sorry. So just one of them. And then here, the question is find the temperature at which the largest number of eggs hatches. So while we're finding a global max, we're actually looking for the T value that goes with it. Okay, so take about 5 minutes, try out these 2 problems. You don't have to do them in this order. You can do them either one first, and then we'll go through them together. All right, take about 30 more seconds. All right, so let's take a look at these. So for the first one, we have some different variables than we usually use, but the process in math is still the same. So hopefully that didn't trip you up too much. But the scenario here is that the number of eggs hatched is related to the temperature in degrees Celsius. And we want to find the temperature at which the largest number of eggs hatch. So the hatch is the H, so we're trying to maximize that. So again, we start by finding critical points. So when we take the derivative of our function, we're going to get 6t squared minus 90t plus 264. And we want to know, when does that equal 0? So again, you can factor this, or you can go ahead and do a quadratic equation. It's really up to you. I factored it. So first I pulled out the 6, and I was left with a t squared minus 15t plus 44. And then I was thinking, what two numbers will multiply to give me 44, but add up to give me negative 15? It took me a minute. But if we use negative 11 and negative 4, 11 times 4 is 44. And since they're negative, they will add up to give me the negative 15. So that becomes 6 times t minus 11, t minus 4. So that means I have a critical point at t equals 11 and t equals 4. So I want to go ahead and see if those are on my interval. So my interval here is 3 to 15. So 4 and 11 are both on that interval, so I can use both of them. Okay, so now I want to make a list. So t equals 11, t equals 4, t equals 3, and t equals 15. And again, the 3 and the 15 come from my interval. Now I want to find out what the dependent value for each of those is going to be by plugging each one back into the original function. Okay, so again, I just did this on my calculator. When you plug in an 11, I got h equals 121. When I plug in 4, I get 464. When I plugged in 3, I got 441. And when I plugged in 15, I get 585. Okay, so once I have all these values, I want to remind myself what the question is, which is find the temperature at which the largest number of eggs hatch, or the largest number of eggs hatches. So I look for the largest value. So my global maximum is 585, but the question is, what is the temperature? So it wants to know the related temperature. So to answer this question, I'm going to report this as 15 degrees Celsius. That is the temperature which gives the global maximum of 585. Okay, this one didn't ask for a global minimum, but if it did, that would happen at one, or that would be 121, right? That's the lowest number. So that's what that one looks like. Hopefully that went okay. For example 3, we want to find the global maximum of this function. And so right off the bat, I noticed that I have one function over another one, and I'm thinking already, I'm like, okay, for critical points, I'm going to have to use a quotient rule. So as I start thinking about critical points, I'm going to set up a quotient rule on the side. So remember, your top function is f, your bottom function is g. We want to find each of their respective derivatives, like this. And then we're going to plug that into the quotient rule to find the first derivative here. So the quotient rule says we're going to do f prime times g minus g prime times f, all divided by g squared. Okay, I'm going to do a simplification step here because I am using the derivative to find something. So I have an x squared plus 1 minus 2x squared. So x squared minus 2x squared gives me negative 1x squared. So I have 1 minus x squared over x squared plus 1 squared. And so another thing I have to remember is that critical points happen when the first derivative equals 0, or if the first derivative is undefined. And that happens if you have a denominator that equals 0. So I'm looking at the denominator here, but there's nothing that's going to make this 0, right? X squared plus 1 doesn't have a number I can plug in that'll make it 0. So I don't have any critical points from it being undefined. So instead, I can look at the numerator and see where does that equal 0, right? That's our regular critical point plan here. So I bring the x squared over, and I have 1 equals x squared. And so my critical points here are x equals 1 and x equals -1. Okay. Once I have my critical points, I want to look at my interval. So my interval is from 0 to 2. So what I notice is that one of my critical points is not on that interval. So x equals -1, I can't use because it's not between 0 and 2. So now I make a list of the values I can use. So x equals 1, x equals 0, and x equals 2. I'm going to plug each of these back into the original to get the dependent value. When I plug in a 1, I get 1 over 1 plus 1. So that's half. When I plug in a 0, I get 0 over 1, which is 0. And when I plug in a 2, I end up with 2 over 5. So I have my y values, and in this one, I'm looking for the maximum. So the biggest value. And so 1/2 is bigger than 2/5 is bigger than 0. So here, my global maximum equals 1/2. Okay. So again, just be really careful with your algebra as you set things up. And especially as we noticed here, you have to make sure that your critical points are on your interval. If they are not, you cannot use them because we're only looking at values between 0 and 2. So these are sort of your common algebraic examples where we're calculating things to find the global max and min. There are some more conceptual ways that we talk about this and try to figure out different things about global maxes and mins. And so we're going to look at 2 examples that don't require computation, but instead require you to think about the information you have and figure out how to apply this idea and definition of global max and min to that information. Okay. Okay. So for the next example, we have g of x is a continuous function that has exactly 1 critical point in the interval -3 to -2. Okay, so that's an interval, not a point, and it's got closed brackets, so we include the endpoints. Find the x values at which the global maximum and global minimum occur on this interval, given that g prime of -2 equals 0 and g double prime of -2 equals 3. So what we have to do is really think about how all this information works together to help us understand the behavior of this function. So one thing I really want to emphasize here is that we don't know what the global max and global min are going to be. We are trying to locate where they happen in terms of x values. So I'm going to give you 2 minutes to think about this. And what I really encourage you to do is think about if you can draw what's happening between -3 and -2 based on the information you have. So these last 2 statements are really important, and we have to remember what they tell us about what the picture looks like, what it's doing, what might be happening. And so take 2 minutes, see if you can work out where the global max and global min might be on this interval, and then we'll talk through it together. Okay, take about 30 more seconds. All right, so let's think about the information we have and what it's going to tell us about what this picture may look like. Okay, so the first thing I want to talk about is the second derivative. So the second derivative at -2 equals 3. The second derivative, if we are talking about the relationship between the second derivative and the original function, is going to tell us the concavity. So since the second derivative at -2 is, yes.
You froze again.
Okay. Yep. So saying we should think about the relationship between the second derivative and the concavity of the original function. So since the second derivative is positive, right, this +3, that's going to tell us that our function is going to be concave up. Okay, so at -2, our function should be concave up, so it should bend upwards. Now, we also know that our function is existing between -3 and -2. And then we know that g prime of -2 equals 0. That means that at -2, we have a critical point, okay? So here, because this is a continuous function, we know that that means we have a horizontal tangent line at -2. We also know that there's exactly one critical point. So since we are concave up and we have a critical point at -2, that's going to be a minimum, right? So this is one of our derivative tests. And so I want to point out that if we have a minimum, there's a couple of ways that can look, right? And even though we are only looking at the interval from -3 to -2, that doesn't mean the function doesn't exist outside of that, but we're only focusing on the part between -3 and -2. So I'm going to go ahead and say that the function has to look like this between -3 and -2. But you might be thinking, how do you know it doesn't do all sorts of crazy things between -2 and -3? So maybe you believe me that we're sort of concave up here, but maybe you're wondering, how do I know that I don't do something like this, right? And my answer is because we only have one critical point. So if we were to turn around at all and stray from this idea of like this just increasing concave up, what would happen is we would create other critical points. But we know that there's only one critical point, so it can't turn around. Now, there is one alternative that could happen. So -2 to -3, we could change the concavity like this. That could happen because we know we're concave up at -2, but we could be concave down over here. However, that will not change the global max and min on that interval, okay? So it could look like this, or it could look like this where it changes concavity. But in both cases, if we are just considering the interval from -2 to -3, this part here, this part here, the highest point happens at -3 and the lowest point happens at -2. So I would say the global max, I'm just going to call it G max, happens at x equals -3. It's got to happen at -3. We got to be going up in order for this critical point to be a minimum. And the global minimum happens at x equals -2. So by figuring out what the picture has to look like, that's going to give us enough insight to figure out what is the global max and what is the global min. Okay, so hopefully that makes sense. You know, when you have these types of situations where you have information about one function at certain points, it's really helpful to draw what's happening if you can, because usually it's like the properties of these drawings that are impacting, you know, the information you're trying to figure out. Okay, so for the next one, we're going to be looking at this function here. So hopefully you can see that okay. I tried to darken it up with red. And so what we're doing is we're looking at this picture and we are trying to approximate the global maximum and minimum on 3 different intervals. Okay, the first interval is the entire function, so -1 to 1.5. So what is the global max and what is the global min? So remember, these are the y values. But then we're going to look at different intervals within this. So what if now we look between 0 and 1? And what if we look at between -0.5 and +0.5? So you're going to try to approximate these values. Some of them are easier to figure out than others. Just do your best to approximate. So I'm going to give you about 2 minutes to see if you can think about what those are going to be based on the picture, and then we'll go through it together. All right, take about 30 more seconds. All right. So the first interval we're looking at here is the entire interval. So from -1 to 1.5, that's the entire picture. So if we're thinking about where the global max and global min are, we're looking for the highest and lowest point on this entire graph. So here is the highest point, here is the lowest point. The highest point, to me, looks a little bit above the halfway mark. I'm going to call that 1.6. And then this is right at 0, right? So the 0 point. So here, I would say the global max is approximately 1.6. And if you said 1.5, 1.7, right, it's all an estimation. So roughly right around there. And the global min is going to have that y value of 0. So that's what I get when I'm just considering this whole entire graph, right? For part B, I want to focus in on what's happening between 0 and 1. So 0 is here, 1 is here. So I'm just going to kind of trace over this. Right? And it looks like this little pocket right here. So what I notice is that the maximum value at both endpoints is going to be 1, right? So that y value of 1. So my global max is 1. And then my global minimum happens at this little critical point right here, right? So down here, and I would say that that's approximately, I don't know, 0.8. Maybe you said 0.9, 0.7, right? But somewhere a little bit less than 1 is the lowest point on this little chunk right here. And then finally, the last interval, we have negative 0.5 to positive 0.5. So let's see, halfway is right about here. And then positive 0.5, roughly here. So we're looking at this interval right here. Okay, so the global max is the same one that I think I saw over here, which is approximately 1.6. And the global min happens again at this little divot from the last one, which I said was approximately 0.8. So one thing I want to caution you about is if you were given a picture and you were asked about the global max and min, you don't want to assume that you should be looking at the whole entire picture. You should look to see if there's a specific interval that you should be looking at, because sometimes you're just asked about a sub-interval. So you just have to focus in on that particular interval to answer the question. Okay, so that's how we would approach it if we had a picture and we were thinking about global maxes and mins. And then our last problem has some algebra in it, but it's also about sort of interpreting the problem to understand what we're trying to find, doing the derivatives and using things we know about the chain rule to answer the question here. So I'm just going to read the question out loud. I'll give you a chance to work on it. And then obviously we'll go through it together. I am going to write it a little bit bigger. Give me 1 second here. So the question says, for time t greater than or equal to 0 in days, the rate at which photosynthesis takes place in the leaf of a plant, represented by the rate at which oxygen is produced, is approximated by P of t equals 100 e to the negative 0.02 t minus e to the negative 0.1 t. Okay. And the question is, when is photosynthesis occurring fastest? And what is that rate? So the second part of this question, what is that rate? That is the global maximum that we're looking for. And the when is the associated t value. So again, we're going to use the same process we did before. We're going to find critical points. Then we're going to make sure they're in our interval, which is here means it's positive. Then we're going to test our critical points. I should say critical point. There's only going to be one into the original function, and that will give us the corresponding rate. Okay, the tricky part here is finding the first derivative because we both have to use a chain rule for these e terms, but then some really sort of tricky algebra to solve for t. So I want you to be really careful about that. And as a general reminder, if you take the derivative of e to some constant times x, the derivative is ce to the cx. So that constant comes out front when you take the derivative. So that's going to happen here for these e terms. Okay, so I'm going to give you about 4 minutes to try this out, see if you can figure out the algebra, find the first derivative, try to find the critical point, see what you can figure out, and then we'll go through it together. All right, take about 30 more seconds. All right. So when we take the first derivative of this function, the 100 is a constant multiple, which means we can take the derivative of each term individually, and the 100 will multiply the derivative of the functions. So for the first term, this negative 0.02 comes out front, everything else stays the same. Similarly, for the second term, we get the same thing back, but a negative 0.1 comes out. Since the negative is in the power and there's a minus here, this negative will cancel this minus when it comes out, making this a plus. So we have 100 times these derivative terms equals 0. Well, in order for that to equal 0, the stuff inside of the parentheses would need to equal 0. So all I did is just rewrote the stuff in the parentheses. So if that equals 0, what I did is I brought this term that had the negative to the right so that I have a term on each side. So my next step algebraically is I'm going to combine the constants on one side and the e's on the other side. So what I'm going to do is I'm going to divide both sides by 0.02 so that I can get rid of the constant on the right. And full disclosure, it doesn't matter which way you do this. You could divide both sides by 0.1, right? We just got to get all the constants to one side. So that's my first step, was to deal with the constants. But then I'm also going to divide so that my e terms are on the same side. Since my constants ended up on the left, I'm going to bring my e's to the right. So I'm going to divide both sides by e to the negative 0.1t. Okay, so that'll cancel on the left, and this is what's left on the right. Okay, so now on the left, I have 0.1 divided by 0.02. If you were to plug that into your calculator, that would become 5. Okay, now on the right, I have e to the negative 0.02t divided by e to the negative 0.1t. We have a rule in algebra that if your functions have the same base, you can subtract the powers to simplify. For example, if you have x to the 6th over x squared, that can become x to the 4th because you do 6 minus 2, right? Same base of x. We're going to do the same thing here. So here we have our e, and so we're going to do negative 0.02t minus negative 0.1t. We're going to subtract the powers, top power minus bottom. The minus and the negative cancel, and that leaves me with a 0.08t. That's the difference between 0.1 and negative 0.02. When I add those two numbers together, I get positive 0.08, and then the t is the same. So this step is really tricky, this combination step. This is where people usually fall apart, and they're like, I don't remember what to do. So this is an important step that if you didn't remember that from algebra, which is totally fine because you may have taken algebra a long time ago, you should write that down or star it or circle it. Okay, how do we solve for t? We take the natural log of both sides. So the natural log of 5 equals the natural log of e to the 0.08t. On the right-hand side, the power will come down out front. So the natural log of 5 equals 0.08t times the natural log of e. But the natural log of e is 1. Anything times 1 is just itself. Finally, we're going to divide both sides by 0.8. So we have the natural log of 5 divided by 0.08 if you turn that into a number, where did I write it down? I believe it's 20 points something. I wrote it down somewhere. 20.11. Okay. So you turn that into a decimal, and that answers the question when. In order to answer the question what, you need to take this 20.11 and you need to plug it all the way back into the original function to get the corresponding rate. And when you do that, you get P of 20.11. That's going to give you 53.499. Okay, so the algebra on this is a little tricky, but those are the steps. Think through it, make sure that makes sense to you. If it doesn't, stop by Drop and Help, and they will help you with that. Okay, I'll see you guys next week. Sorry for keeping you over by a minute. Have a great rest of your week.